in Barcelona as a Marie Curie Fellow to work with Antonio Azin. Last year, he moved to Barbara Terhal's group at Delft University of Technology. And today he's going to tell us about nonclassicality, quantum engines, and quantum metrology. So I think with these words, I'm going to hand over the virtual floor to you, Matteo. And thank you very much for agreeing to come and give this talk at the Cavendish Hitachi Quantum Information Seminar. Thank you.
Thank you very much, David, for the kind invitation and the opportunity to give this talk. And thank you all for coming. I hope you're doing okay in these circumstances. So today I'm going to talk about contextuality, and in particular, the way in which contextuality affects actual physical processes. And yeah, let's see how far I can get. I'll try to stick with the timetable of a 30 minutes kind of overview. But yeah, if you're interested in more details, these are the details for it. So let me, before I kind of jump into some of the details, let me just give you a very general context of this kind of research lines, which are a research line that looks for signature of strongly quantum phenomena in quantum experiments. So the basic idea is relatively simple. So you're imagining that you've got your, your favorite quantum devices and, performing a certain set of operations, preparations of certain states, dynamics, and at the end, measurements. And at the end of the day, what you're going to do is collect a set of outcome statistics. So you're looking at a set of correlations between your outcomes. And what I'm imagining here with this picture is that essentially you are imagining that the set of your all of your possible outcome probabilities that are generated by your quantum experiments, you imagine each of them as a point in some abstract space, no? Which is what I denoted here by Q, no? And you're kind of filling up this space, which is the set of all possible correlations that you observe in your experiment. On top of that, what you're looking for is explanations or mechanisms that are able to generate those distributions. So, so what you probably have in mind is some notion of classicality. And just to be a bit more concrete, imagine, for example, what's probably the most famous notion of classicality, which is the idea that you're looking for underlying mechanisms that are behaving locally, and this is the famous Bell locality. And what you're then trying to ask is basically what kind of correlations can be generated only through those mechanisms. And this is what I drew here by this set C here. Now, these are the kind of correlations that can indeed be explained by mechanisms that satisfy your favorite notion of classicality, say locality, for example. But then, of course, we also know that quantum mechanics, in the case of locality, admits also, you can generate experiments that cannot be explained that way. And indeed, the basic idea, once you define a notion of classicality, is that you're looking for inequalities whose violation signals the fact that that particular experiment cannot be explained under that notion. No? And in the case of Bell inequalities, for example, what these basically are, they are separating hyperplanes between this set C, the set of things that can be explained classically under your notion, and the rest of the quantum distributions. So that when you see a violation, say that you are on this side of this separating hyperplane, and then you know for a fact that in this case you cannot generate that distribution locally. But of course, this kind of general reasoning can be done also for different notions of classicality that you may want to use as a benchmark for your experiment. So, so one question that you may ask is, why would you do that? I mean, why would you ask these kind of questions? And I guess there are various reasons, and here I mention a few. One is, of course, a foundational reason, as you can imagine, but there are other reasons too. One is, for example, the idea that you would like to certify the fact that in your experiment there are quantum resources that are at play. No, This is, for example, most notably the case of the notion of self-testing, where you're using the correlations to infer certain properties about your underlying state, no? And one trivial inference that you can immediately make, for example, is that if you're, in this case, again, for localities, that if your distribution violates a Bell inequality, then necessarily the state that you're using or that you're probing is entangled. No? So you can kind of reverse the idea and use the fact that there is a violation to certify the existence of certain quantum resources in your device or in your experiment. Another kind of famous reason is that, okay, maybe what you're gonna do is you're gonna define certain information theoretical tasks or games, no? And then you're asking the question, well, now that I know that there exist distributions that are up here, that they cannot be generated, classically under this notion, what kind of impact does it have on the performance or the maximum winning probability of certain games? Now, this is, for example, the case, say, in communication complexity, where you want to know how many bits two or more parties needs to exchange to compute a certain function. And there are, of course, many other examples. And finally, in this, I guess, list at least, one reason that you may wonder about, one reason why you may ask these questions is you would like to understand what's the impact on actual physical processes of the existence of these correlations that defy classical explanation. No? And the kind of place where I'm coming to these questions is actually that, as David was saying, I studied thermodynamics in my PhD, and I always wanted to understand the fact that there are these highly non-classical correlations and highly non-classical distribution. What's the impact on, say, thermodynamic processes? You know? And you can ask this question, of course, on, it's kind of similar to the third one, but more with a physical flavor to it, if you want. Okay, so this is very general, but the kind of question that I'm going to ask and the kind of classical notion I'm going to use is the notion of non-contextuality, okay? This is a different notion from locality, and I'm gonna give you a quick introduction of what it means, but then the basic reasoning, as you will see, will work very similarly. We will want to identify inequalities whose violation tells you for a fact that your experiment is showing a phenomenon that cannot be explained under that, in this case, by a non-contextual model. And in particular, it would be nice if this kind of inequality is not just some random inequality, but it's actually an inequality involving the performance of some device, or as it will be in this case, some physical property, the way a certain physical property is behaving. And in particular, again, to be more precise, the kind of result I would like to show you is that under this notion of non-contextuality, there is a limit on how much the average value of an observable can change under a certain perturbation. So here, what you are imagining is that you got your quantum system, you're doing a small perturbation, and you're looking at some fixed observable that you're interested in, how much that observable is changing. And quantum mechanically, it can happen that change is linear in G for small g, for so small perturbations. This can be linear in the perturbation strength, whereas we're going to see that in non-contextual models, there is a quadratic kind of behavior. So therefore, this small enough, you will see a violation. Okay, so that's where I want to get to, basically. But I need to introduce the various ingredients, of course. And but yeah, so this is the basic takeaway that I'm going to try to show you, that quantum linear response can be contextual, and that this has applications to thermodynamics, metrology, and other situations as well. All right, so let's start by introducing some of these ingredients that I need to introduce. And the first one is, what does it mean that a certain quantum experiments admits a non-contextual explanation? So I need to kind of define what this red set is, this classical set I was showing you before. And to do that, I first need to to quickly tell you about the notion of ontological models, which is, well, basically it's the same as hidden variable models if you're more familiar with that kind of notion. What ontological models are a set of explanations for your experiment, which are basically stochastic explanations of what's going on. So what I drew here are 3 boxes, which are kind of representing schematically your quantum experiment, where there is a phase where you're preparing a certain quantum state. This is this box P. Then there is a phase where your quantum state is evolving under certain dynamics, and maybe some, Schrödinger evolution, or maybe some open quantum system dynamics, but there is some transformation going on your system. And finally, there is a measurement, which is this last box, where you're performing a measurement and you're getting some outcome K with a certain probability, okay? And what an ontological model is that it's an association to each of these elements to a particular kind of stochastic object. So in particular, what is that you're imagining is that whenever I'm preparing my my quantum state, in this case, what I'm actually doing, or at least what the ontological model, the way the ontological model describes what's going on, is that what I'm doing is I'm sampling from a certain probability distribution that lives in some abstract space of physical states, lambda. So these are lambdas, okay? And these lambdas can be essentially whatever they want under some really minimal conditions, but you can, if you want to have some idea in mind, you can imagine that these lambdas may be just the points in, coordinates in phase space, or they could be coordinates in configuration space, or well, really they can be whatever you want, no? So what you're imagining is that every time I'm preparing my state, I'm actually sampling according to some probability distribution P of lambda, okay, on this set of physical states. So what's actually going out of this box is some lambda here, okay? So the lambda travels to the transformation box, and what's a transformation box in kind of generality in these kind of models? Well, this is just an update probability. So the transformation box is going to be represented by the conditional probability that given that the state lambda comes in, some state lambda prime comes out, okay? So here you have lambda prime coming out, and this is just this update probability. And finally, what's the measurement? Well, again, it's gonna be represented by a set of conditional probabilities, and it's going to be the probability that you're going to output outcome K, given that inside the measurement box, the state lambda prime entered, okay? And of course, at the end of the day, what is it you're actually observing in the experiment? Well, what you're observing is just probabilities that you're getting outcomes K, given that you follow this kind of procedure where you prepared according to your preparation box, your quantum state, and you transform it according to this transformation box, and then you measure it according to this measurement box. No? And this is what you're actually collecting in the experiment. You're doing statistics on this. But how is the ontological model explaining these kind of statistics? Well, quite naturally, just by propagation of probabilities, no? Because what you actually have is that, with some probability you prepare lambda, times with some probability, given that you prepare lambda, you're gonna jump to lambda prime, times with some probability, given that you are in lambda prime at the end, you're gonna output the outcome K, okay? And of course, you just have to average over your ignorance about what exactly the initial lambda was. So I'm gonna sum over d lambda and d lambda prime, okay? So this is how ontological models kind of give you a possible mechanism to explain what you actually see. So this is what you actually see, and this is the kind of mechanism that you're trying to use to explain what's going on in your experiment, okay? And these are also essentially called also hidden variable models. There is just slight difference between the two notions, but it's essentially the same. And okay, so this is what ontological models are, but of course this is not the whole story, because ontological models actually are very, very general. So you can explain any quantum statistics that you want using a general ontological model. because this can be, you know, for example, it can be the lambdas can behave non-locally in any way they want, say, for example. And yeah, it's so general that it can explain everything. So what you need to find is some notion of classicality that is going to constrain this set of ontological models. So Bell introduced the notion of, you know, locality, and the notion that I'm gonna look at here is the notion of non-contextuality in a generalized fashion. And to kind of get to that notion, I think it's nice to go back for a second and imagine actually a classical system. So what I drew here is just a classical mechanical system, and you know, on this axis, this is some multidimensional phase space. So there is some axes that are just denoting the positions of a set of m particles, and you know, other directions are denoting the momenta of those particles. And in general, when I'm preparing some state classically, what I'm actually doing is that I'm preparing some probability distribution in phase space. Okay, that could be a point or could be a distribution. So imagine that now I'm doing two different experiments. In one case, I'm you know, preparing a distribution according to this kind of red blob, and in another case, I'm preparing a distribution or an ensemble, if you want, according to this blue blob. Okay, and then you would agree that you know, as long as these two blobs are not actually exactly the same, there will be an experiment that can tell apart these two different ensembles, no? And why it's so? Well, that's in a sense very intuitive, is that okay, even if the two distributions coincide here, say where they overlap, you know, sometimes they will, you know, I will, you know, get a point that is actually only compatible with the blue one, and sometimes I will get a point that it's only compatible with the, you know, red blob, and then there will be some measurement, maybe complicated one, but in principle, there is a measurement that can tell these two apart, as long as I collect enough statistics. So this is what I'm writing essentially here, is that, well, there is some experiment. So here, you know, graphically, there is some measurement box such that if I send in particles that I'm sampled according to the blue ensemble, they will give me some probability distribution over the outcomes. And if I send in the particle, an ensemble sample according to the red one, will give me a different you know, distribution over the outcome. So that if I collect enough of these samples, I can be, you know, as sure as I want about the fact that you prepare either the blue or the red ensemble. And so what non-contextuality is basically kind of elevating this very natural situation to a principle. So the principle is that differences in the physical state can always be experimentally detected. So there shouldn't be differences in the way I describe the underlying physical states that have no empirical consequence. That's just, in a sense, the definition of a bad, you know, a bad theory, you know, because in a sense, if you think about it, the way you can criticize, say, Newtonian mechanics and absolute space in Newtonian mechanics is exactly that. That, you know, there is this whole structure that has actually no empirical consequence. So if I translate my whole, you know, toy universe in absolute space, there is nothing I can do to actually detect that happened. So that structure is actually kind of a spurious structure, and I probably want to eliminate it from the theory. So the notion of the non-contextuality is the following, the one I just mentioned. Difference in physical states can be experimentally detected, but you can also write it, and that's actually the way you will find it in papers. You kind of do the counter positive of that statement. It's, if no experiment can tell two systems apart, then those systems are in the same physical state or the same distribution over physical states. Okay, which is, you know, basically the idea of Leibniz's idea of identity of indiscernibles. If two things cannot be told apart by any experiment whatsoever, it must be because their underlying physical state is actually the same. So that's the basic idea of non-contextuality, and that's a, kind of the principle that is going to constrain the set of, you know, distributions that I can get out. No, I'm only looking at mechanisms that satisfy this kind of principle. Okay, so I gave you an idea of how I'm gonna construct this red set, the set of classical set of the distributions that admit a classical explanation. And now I just need to tell you what kind of experiment I'm actually gonna look at. It's not just a generic quantum experiment. I'm gonna look at an experiment where you're doing a small perturbation on a quantum system. So this is the realm of quantum linear response theory. So again, by sticking to the box picture, you got three boxes. The first box is now in the quantum description, just the one preparing your quantum state. The second box is the one that it's inducing some perturbation. So I denoted this perturbation as some V of t. So this is some change in your Hamiltonian. And then I stick in front a prefactor G, which is just the strength of this perturbation. So I'm going to be interested in particular in what happens for very small g. And finally, I'm measuring some observable O. Okay, and what I'm interested in is how much the average value of the observable O has changed due to the perturbation compared to what it was before I actually implemented the perturbation. Okay, so this is something that, of course, you can compute in quantum mechanics quite easily. And this is the kind of answer you get out. I put an asterisk here just to say this is all in interaction picture, even though I don't actually put the labels every time for interaction picture. But okay, there is some expression that tells you how much the average value of O changes due to the perturbation at first order, at the first non-zero order in G. And what you see in this expression, I guess the only thing I would like you to focus is that this change can actually be linear in G. Okay, so basically, you definitely need some non-commutativity going on. So you need that the perturbation doesn't commute with your with the observable of interest. You need that these things do not commute with the projector on your initial state. But definitely, as long as this expression is non-zero, then you're going to have a quantum response that is linear in G. Okay, plus corrections that are of higher order. So the basic picture is this one, that yeah, I mean, simply that for G small enough, my quantum linear response can be indeed linear in G. Okay, and that's all. So now that we know that that's the case, what we need to do is to compute the same quantity, but in a generic, non-contextual ontological model. So yeah, that's what I was saying, that's all in interaction picture. So let's go back now to a generic ontological model. So I have the same experiment, okay, but now I'm describing it through the ontological model. So once again, just to remind you, I'm preparing the quantum, instead of preparing the quantum state, I will have that I'm sampling according to some probability distribution. Instead of having some transformation, in this case, say a unitary transformation, I have some update map of my state. And of course, this update map can depend on G, the strength of my perturbation. And finally, I've got the response function that tells me with what probability the outcome that I output is K, given that the state was lambda prime at the end. All right, so how do I explain then this change in average value of O in this ontological model? Well, it's, this is the expression, looks a bit messy, but actually, if you can just follow what's going on, it's essentially what I said here in Word on top, no? You're just following what's happening in the state. And so this is the probability that you have output K, given that you prepare lambda. Well, I guess this is without the P. So this is the overall probability that you're outputting a certain K, and then you're just summing over, OK to get the average. So this expression on the left is just the average value of O after the perturbation. Whereas this guy here on the right is exactly the same, but without the perturbation. So as you can see, this is indeed the change in the average value of O according to the ontological model. But up to now, I didn't say anything. I mean, this P of lambda can be whatever it wants. This PG can be whatever it wants. And, everything can be whatever it wants. So what I need to do is to kind of restrict the freedom is that I need to use my notion of non-contextuality, okay? But remember that what I need to actually apply the notion of non-contextuality is that I need to identify two things that are operationally indistinguishable, and then I'm going to use this principle to claim that they should be represented exactly in the same way in the ontological model. Okay, so they should be physically identical. So what are these two things that are actually indistinguishable? And this is what they are. So I'm gonna walk you through now this picture here. So what I drew here on the left and on the right are two transformations. No? This is, if you want, T1 and T2. And what I'm gonna claim is that in certain linear response regimes, these operations are indistinguishable, meaning no matter what quantum state you put in input and no matter what measurement you do in output, you get exactly the same statistics in both cases. So what are these transformations? So the first transformation, T1, is one where when the particle goes in, I'm tossing a coin, and with probability 1/2, I'm just sending my particle through the linear response unitary, so meaning that it's going to be updated by this probability distribution. And with probability 1/2, I'm sending it through the inverse of that unitary. So I'm sending it through U dagger, say, okay? And this U dagger, this inverse unitary, is gonna be represented by some other probability distribution, P tilde, okay? Okay, and that's all. So I'm just, basically with some probability, I'm doing the experiment, the linear response experiment that I demand, and with some probability 1/2, I am just doing the kind of the same linear response experiment, but with the inverse of the unitary instead of the unitary itself. And the claim is that if I do that, actually this situation is indistinguishable from the one on the right. And the one on the right is one where basically with probability that is almost 1, so probability that is 1 minus corrections of order G square, I just do nothing. So, and with a small probability, which is probability of order G square, I just do some other channel, some other map, some other quantum operation on my system. So what this equivalence is telling me is essentially the following, that if I mix my linear response unitary with its inverse, this is almost the same as inverting the unitary, no? So essentially up to corrections of order G square, it is exactly the same as inverting the unitary. So that's why I'm calling this kind of property stochastic reversibility. So the transformation on the left and the transformation on the right cannot be distinguished by just looking at the outcome probabilities of any experiment, no matter what quantum state I prepare and what measurement I do. So they are operationally indistinguishable. And according to the principle of non-contextuality, then the update map 41 and the update map 42, they should be exactly the same, okay? So in this particular case, what's the update map on the left? Well, this is just with probability 1/2 is this update map, the update map for my perturbation. And with probability 1/2 is just the update map for the inverse of that perturbation, whatever this update map is. And this should be exactly equal. And this is where I'm using non-contextuality to, well, with probability, which is almost 1, so 1 minus correction of order G square, I'm doing nothing on my state. And with probability that is something of order G square, well, I'm doing something else that I'm denoting by C of lambda prime given lambda. Okay, so this is where I'm using non-contextuality to go from this operational equivalence to the fact that also the underlying mechanisms are the same in these two cases. So now I have all of the ingredients I need to actually tell you what the main result is. So the main result is this non-contextual bound on linear response. So the result is, suppose that your perturbation satisfies the stochastic reversibility. then in any non-contextual ontological model, the response of your observable cannot be bigger than something that goes as order G squared. So I'm kind of going back to this initial picture where in quantum mechanics, I can have a response which is of order G, whereas I have a non-contextual bound that is of order G squared, so that if I take the perturbation small enough, the latter is gonna be below the quantum response, so that I have a violation. So meaning that what's going on is that quantum mechanics is giving a response that is too large to be explainable by a non-contextual invariable model. So that is what is going on. Okay. So now, if you look at this result, there is still a problem, which is I don't know when is it that I can use it, because there is this funny stochastic reversibility assumption, and when is this property actually satisfied by your favorite linear response experiment? And okay, so what you need is a way to test if your linear response experiment satisfies this property, so that this inequality applies. And there is a technical lemma for it, which is giving you sufficient condition to be sure that stochastic reversibility in linear response is satisfied. So this is a test that involves the eigenvalue of this integral of the linear response of the perturbation, which is, by the way, something that you need to compute the first order perturbation in quantum mechanics. And and then there is a test that involves the eigenvalues of this operator. And if you check that, if you can use the test, and what happens is that for dimension 2, this test is always satisfied. So basically, the stochastic reversibility is always satisfied if you're doing linear response experiments on a single qubit. However, for dimension 3 and higher, you actually need to kind of look at your particular scenario and apply this test to see if the stochastic reversibility property is satisfied or not. So that's a basic idea. So you run the test, and then if the test tells you yes, stochastic reversibility is satisfied, you know for a fact that if you see a quantum response of order G, you have contextuality in your experiment. So yeah, that's a takeaway message. A linear response of order G in settings that satisfy stochastic reversibility is only possible in contextual ontological models. So it's a proof of contextuality. Okay, so let me just end by giving you quickly an application of this result. And this is an application in the context of thermodynamics. So what I've got here is a two-stroke engine. So the basic idea is that you've got a machine that is trying to extract work from a temperature gradient. So what you got here is that you have, this is a single qubit version of this machine. You got a single qubit, which is sometimes also called a working medium, which is coupled with a hot and a cold bath at the same time. And this first step or stroke, as it is called in the context of thermodynamics, is a partial thermalization. You're partially thermalizing your quantum system. And after this first step, you decouple your system from the baths, and then you do some, you apply some unitary operation, which is your perturbation here to your qubit only, And this unitary operation is extracting from some work from the fact that the system is out of equilibrium. It's extracting some work and putting it into the field. And then you just repeat, and you're gonna check how much power this machine can extract. And the basic picture is the following. It was well known, in particular, this goes back most notably to a paper by Ramuzdin, Amikal Levy, and Ronnie Kozlov, that a quantum coherent engine, meaning an engine such as this working medium, this qubit, after the first stroke contains quantum superposition in the energy basis, is capable of giving you output in terms of work or power that goes as order G with your coupling strength. Whereas if after the first stroke you have no coherence left in your qubit or working medium, which for example it's the case if you completely dephase your qubit after the first stroke, then your power goes down to order G squared. And this was claimed to be somehow a quantum advantage because you're using coherence to improve the power output of this engine. In a sense, the issue with this kind of result is that, well, you're just comparing your quantum engine with, the same engine where you apply strong dephasings between the two strokes. And this is a little bit of a limited comparison that you're doing. But basically, by using this theorem that I just showed you, what you can show is that, well, it's not just only the dephased quantum engine that behaves in this way. It's actually so, meaning it has less power. Actually, it's any engine whose inner mechanism is classical, meaning non-contextual, that will have a power output which goes as order G squared, meaning that now you can really identify or certify this difference between these two different behaviors of these two engines as a kind of genuine quantum signature. So let me go then to these conclusions. So I showed you that under stochastic reversibility, for which there is a test, quantum linear response experiments are contextual. There are certain things I didn't have time to tell you about, which is, for example, what happens in non-ideal scenarios where things are a little bit more messy. They're, the unitary that you're doing in your perturbation is not exactly unitary, but long story short is that you can deal with some amount of noise in this kind of experiment. And secondly, I didn't tell you about a different small application to phase estimation, but if you're interested, I can quickly tell you about it at the end. I showed you instead this application where you have a single qubit two-stroke engine with a coherent working median, and I showed you that this model actually has no classical analog. And finally, it's maybe not good to finish with a bad thing, but I think it's actually important that I've been using this property of stochastic reversibility to prove this result of, this contextuality result. But I think it would be nicer if the kind of property that we are using to prove the theorem is not some extra property that you're kind of checking on a side, but it's something that is more native to the problem you're interested in. Say, if you're interested in quantum engine, some property of the engine itself that is thermodynamically relevant, rather than, as I said, this property that you check on a side. So it would be nice to have alternative proofs as well. So yeah, with this, I kind of conclude this quick overview. If you're interested in more details, this is the reference. And yeah, thank you very much for listening, and I will be very happy to take any questions that you may have.
Okay, thanks a lot, Matteo, for a really wonderful talk. I should repeat for everyone who's tuned in, if you want to ask questions, you could type them into the chat, just as Stefan has done, and then I will promote you to a panelist. So I'm gonna, or Hugo, you're the host, I think, of the meeting. So if you could promote Stefan to a panelist, then he can come on board and ask the questions.
You hear me?
Yes.
Okay, good. Well, thank you for a nice talk. Actually, I have 4 minutes, and then I have to run to another meeting, so I'm very sorry. Thank you for a very nice talk. So I have a question. If I understood you correctly, the non-contextuality criterion or test you have involves only the eigenvalues of V of t, basically, or some integral thereof. Doesn't it depend on the initial state you're using?
So thanks for the question. So what this lemma is doing is that it's checking that it is the case that this particular operational equivalence is satisfied, meaning that if you take your linear response experiment, and I'm gonna call the kind of box of this experiment by t, you can mix it with some other transformation t tilde in such a way that this is, apart from order G square corrections, this is basically just the identity box.
And this is for all initial conditions then?
Yes, it needs to be for every, that essentially whatever initial state you put in and whatever measurement you do, this is the case. So in quantum mechanics, what we would say is that you would need to do channel tomography of this and check that, this channel is actually exactly the same as this channel. This is how it would be phrased in quantum mechanics. And then you can use your assumption of non-contextuality, because now you have two things that are operationally equivalent, and you can claim that they should be represented in the same way in your hidden variable model, which is this notion of generalized non-contextuality due to speckens that I'm using here.
Okay, yeah, but it's important that it's for all initial states, because of course there are many situations where perturbations of order g squared because of the initial state.
Yes. Yeah. Yes. So. Well, it's this particular combination that needs to give you order g squared. So the mixture of your unit. So in quantum mechanics, it would be I mix my unitary with its inverse. And basically, to first order in G, this is the same as inverting the unitary.
Yeah, what I mean is that very often, without mixing for many initial states, it is already order G squared. That's what I'm trying to say.
Yes. So if you do have, if you do have a response of order G squared, meaning that this kind of thing is zero. So if you, because you pick up an initial state, sorry for the going through quickly. Where is it? Yeah. So if for your, due to your choice of the initial state, this is zero, then also the quantum will be like that, and then you will not be able to prove contextuality. So you need to choose an initial state that gives you this order G response, but also you need to check that for any initial state, if you mix your perturbation with its inverse, you get something which is basically the identity up to things that are of order G squared.
Yeah, so what I mean, I agree, I fully agree. So to put it differently, if I've only access to one particular initial state in my whole universe, or only a few, for which it is already quadratic, I may be able to make a hidden variable theory, for example, that fits that state.
Yeah.
That's what you're saying, right?
Yeah.
Okay. Well, thank you very much.
Thank you.
Good to see you, Stefan.
Yeah, good to see you. So I will be running off in 35 seconds or something like that.
Well, enjoy your next meeting and your weekend.
Okay, thank you. You too.
I see that we have another question from Alexander Lasek here. So maybe he could also be promoted to a panelist. Am I the host now? Let's see.
Hi.
Hello.
Hi, Matteo. So I wanted to ask if you can basically have a system that is in between, so it's not fully contextual or fully non-contextual, and then would have some sort of mixed response that maybe would be harder to distinguish. Or for example, per the last question, if the initial state would, let's say, almost commute with that commutator.
So, well, I guess for the latter, what's gonna happen is if it's almost commuting, I guess that this thing is gonna be really, flat in a sense, close to G equals 0, so that you really need to go to very, very, very weak couplings before you're actually able to say it. So there will be a whole region where, if this is your, this is your non-contextual bound. If you're sitting here, you're not going to see anything. You're not going to see anything. You really need to go very, very small G. And how small this G must be depends on, as you said, if it's only very slightly non-commuting, then you really need to go here. And then the difference kind of up in absolute value between this guy and the non-contextual bound is going to be very, very tiny. So it's going to be very difficult to detect as well. And in terms of the first question, I guess here I just looked at kind of, is there a non-contextual model or not? If you want to ask a more refined question, I guess you would need to kind of try to quantify how much something is contextual. and relate that quantity to you know, how much is here violation. And I guess one thing that comes to my mind is that there is an equivalence between the existence of non-contextual variable models and the existence of positive quasi-probability representations in quantum mechanics. So that essentially you could say, well, maybe there is a relation between, say, how much negativity there is and in the system and how much I see a violation. And in fact, you can rephrase this whole guy in terms of a quasi-probability. So yeah, I don't think this suggestion is yeah, I think this suggestion is probably a good one.
Yeah, we did work on negativity with David and Hugo actually. And do you have any estimate of what amplitude of G you would need to go to see the difference between linear and the quadratic here? And could it be, like we said, like, would you know if this is too high to, you know, what is it reasonable? Or maybe the amplitude is so high that it would not be reasonable to reach it within a linear response.
You mean it's maybe too small to, this G is too small
to... Do you have are you able to estimate what sort of G you need to go to see the difference?
Yeah, no, so in general here, no. Basically what you need to do would be to estimate the remainder. I think for simple systems, one could do that and actually estimate the remainder and check what the actual G is. And by the way, I say small G, but you could also rephrase it and say, well, because everything that always appears in this kind of expression is G times time, you could kind of rephrase it as small time that is maybe more natural and, you know, more realistic. You know, say it's a short pulse. But yeah, I didn't do the calculation for a specific system, but I think this would be interesting to do. Yeah.
Okay, thanks.
Thank you.
Okay. When you mention small time, do you don't have an estimate on how small this small time is, right?
Well, yeah, this in a sense, it's exactly the same question.
Yeah, yes, it's the same
G,
question. But
yes.
Could this be some ridiculously infinitesimally small time that's absolutely impossible to test, or do you think that this would happen in some realistic?
I don't think it's gonna be. I mean, the kind of actual bound that you get for this guy here is like P times something that is essentially G squared times something which is the maximum eigenvalue of your observable. And this guy has to be smaller than, something that is, of order G essentially. Okay, this is, I cannot do it here but it doesn't look ridiculous. But one should also take into account that in an actual experiment, you're gonna have non-ideal operations. So your unitary is not actually a unitary. And, whenever you've got these situations, you can deal with them, but there is a bit of space where hidden variable models can hide in the noise that you've got. And for that, typically, you actually need to be quite precise. Now, looking at different contextuality proofs, one can see that you need to be very precise and not like crazily so, like still within the boundaries of what can be done experimentally. So I would imagine that maybe something like that would happen also if you try to do the full calculation, including noise in this kind of settings, that you need to a very precise and kind of clean experiment to see it. But yeah.
So I have maybe just a small comment on Alex's question, and then I have a question or a request myself. And I think the comment on your question, Alex, is that like Nicole and I, we were very amazed by this paper. We liked it very much. And then we liked it particularly because it had these kind of commutators that you could express in terms of Kirchhoff-Dirac quasi-probability distributions. So a cool thing to do would be to go and see if you could like kind of relate the amount of negativity in a KD distribution to where this this boundary between the quantum and classical level would be. And I think with Matteo's tools he presents in his paper, it's probably quite straightforward to do that. I don't know if you agree, Matteo.
Yeah, I think it's, yeah, I guess I would need to think about the exact phrasing, of course, that's non-trivial, but I mean, this is, maybe I think we even talked about this is exactly imaginary part of the Kirchhoff-Dirac distribution, this first order response. So yeah, and then the imaginary part is a signature. The existence of a non-zero imaginary part is a signature of non-contextuality. And of course, here is appearing exactly as a prefactor to your G. So it's telling you how strong actually the response is. Yeah, I think that's in fact, I agree with your comment.
So that's an encouragement to like anyone listening.
Yeah,
like,
I'd be interested in looking at this together.
Maybe we should do that actually. Yeah. Then I have, if you have a little bit more time, I have kind of two requests, Matteo.
Yeah, I do.
I'll tell you both requests, and then you can either pick your favorite or do both. So we have quite a few students attending now, and some of them work on quantum parameter estimation or quantum metrology. I think they might be too shy to ask, but maybe you could say a little bit about how this work relates to parameter estimation.
Mm-hmm.
And then from a personal point of view, I'm in your paper, in one of the appendices, you talk a bit about the quantum Zeno effect. And it's now almost a year since I read the appendices. I reread the paper just before, but if you could, have you thought about like a classical system, like a real like realization where you could get the quantum Zeno effect in a non-contextual model?
Mm-hmm. Okay. Okay, so let me start with the first. So, okay, so phase estimation. So this was a different kind of application of this result. Also, I guess quite straightforward. So the basic idea is that, okay, in phase estimation, what you got is that you got some unitary here, which is generated by some Hamiltonian H. And this unitary is acting, say, no, I cannot, yes. It's acting for some amount of time, or, is giving you a phase shift by an angle phi. And what you're allowed to do here is that you are allowed to choose what probe you're sending in and what measurement you're doing to get an estimate of this unknown parameter phi. And so how does this relate with this stuff about contextuality? Well, the basic idea is that in parameter estimation, what really matters is that if I take a state, I can now kind of define an orbit, which is just basically how the state is changing as this phase changes, no? And what matters is really how much, if I change this phase by a little bit, it matters how much the quantum state is changing, okay? And this is basically what the quantum Fisher information is quantifying, because the biggest the change, the better it is, because I'm gonna be able to, you distinguish very well, even very small changes in my parameter. So now what is going on here is that these all proofs of contextuality are based on the idea that because of, that basically when I think about what happens in an ontological model, what I'm associating to this unitary is some update probability. So I'm I have my quantum system coming in, and this is associated to some probability P of lambda of, sampling from some abstract states lambda. And this guy here is some T phi of lambda prime given lambda. So it's some update probability of my lambda that depends on phi. No? And the basic idea is that basically because of this property of stochastic reversibility, which is, let me take this to be a qubit, so we don't even need to think about it. It's immediately satisfied. What happens is that this kind of response here cannot be very strong in, for small phi. So, or better, maybe I should say delta phi, because what really matters is what happens when I'm changing from phi to some phi plus delta phi. So this is what it's being represented here. And so, and in the ontological model, I'm going to try to distinguish my P of lambda from P of delta phi of lambda, which is just what happens when I, the probability I get once I update it with these conditional probabilities. Now, this is what I'm going, say, from P phi quantum mechanically, I'm going from this to that. And in terms of the ontological model, I'm going from some probability to this other probability. And what's going on is that the change in this probability is actually small. And in particular, it's going to be, okay, it's not exactly like that, but it's essentially that the change, this delta P is going to be of order phi square, okay? So it's going to be not linear in phi, but again, quadratic in phi. So there is still this idea of changes that are quadratic rather than linear when you do a small change, okay? A small unitary in a sense here, which is what happens here. I'm thinking about this unitary that maps me from here to here. So because this unitary cannot induce a big change in the underlying probability, my ability to distinguish the parameter in the ontological model is going to be very small. And in particular, what you can prove is that basically the quantum Fisher information in non-contextual ontological models in these experiments is zero, meaning that then the variance of your estimation kind of shoots to infinity. So yeah, so I'm not sure I've been super clear. I try to be quick, but maybe I
think it's a good overview. Like if someone is really interested, they should go and read the paper.
Yeah, but yeah, feel free to email me if you want. I will try to explain it kind of a bit more step by step.
Maybe just a quick question on this. So from a egoistic point of view, when I teach weak values, I used to refer to this result of Matthew Pusey saying that like if the weak value is anomalous, then it's non-classical in that it's contextual, the experiment. But like kind of any weak value experiment you could rephrase as a phase estimation experiment. So, and I might have asked you this before, but so does your result imply that a weak value experiment where the weak value is not anomalous is also a proof of contextuality?
So I think if the weak value is not anomalous, meaning the imaginary part is zero in this case, then your response, the response of your quantum system is going to be quadratic itself, not the quantum response. So it kind of goes back to this formula we were talking about before. Now, what's a change in some observable O due to some small perturbation in quantum mechanics? And now you can actually, you can write it down, and then you can actually identify that this quantity contains the imaginary part of the weak value. You can just do a rephrasing. Now, if this imaginary part is zero, it means you're in the situation where also the quantum response is quadratic, and then you don't have any proof of contextuality. So you need to have an anomalous weak value to run this contextuality proof in a sense. Even though these are contextuality proofs, they are quite different in the sense that what's been proven to be contextual in the work that then we extended also to the imaginary part, also with math, is that the experiment that probes a weak value, so the whole experiment where you take your system, you couple it with some pointer, and then you do a post-selection, this whole thing is contextual, but this is not immediately related to, say, quantum linear response, for example. No? I mean, this imaginary part inside the quantum linear response, I can measure it by this other experiment, and the outcomes of that experiment are contextual, but it doesn't mean that the linear response itself, is contextual. So that's maybe the relation. Yeah.
Yeah, I don't know if you have something quick to say about the Zeno effect, but otherwise maybe.
Zeno effect, maybe, very quickly. Same. Okay, I'm gonna use this idea, even though it's not quite correct. But the whole idea here is that you need this property of being stochastic. You need this property of stochastic reversibility that basically tells me, when I take my unitary and I mix it with its inverse, I get something which, with probability, apart from something of probability order G square, is the identity operation, plus something else. So so then what's natural? So a natural way to ensure that this quantity that this relation is satisfied is to take the response in the ontological model to be quadratic. So for small g, it's natural to say, well, this is maybe just basically the identity apart from something which is of order g squared. So here there is some other c of lambda prime lambda. So this is a natural way to ensure that this property is satisfied. But then if you do that, what you see is that you're inducing for small, and this g, remember that we can think about it as time as well. So if you take this model now that naturally satisfies stochastic reversibility, so meaning it satisfies stochastic reversibility, and in fact it is non-contextual, because if I mix this and the inverse, I can define the inverse in a way that the equality is satisfied. So if you take this model will have a Zeno effect, in the sense that what's happening is that, or you can construct the model in a way that you have a Zeno effect, because what's happening is that the unitary, or which is here represented by an update probability, just gives you an order t square change. But if you're doing every amount of time, which is some t over n, you're doing a measurement, so you're re-preparing the initial probability, then you can run through the calculation, which is analog to the standard Zeno effect calculation. You see that what's going on is that with probability that is as close to 1 as you want, you are not doing anything in the experiment, where you're just doing a tiny unitary, and then you measure, and then you're doing a tiny unitary, and then you measure, and so on. This is gonna be doing nothing if your update probability satisfies this. So bottom line is, to be non-contextual, it's natural. What we have seen is that to be non-contextual, it's natural to think that the response is quadratic. But then if the response is quadratic, you're gonna have a Zeno effect. Maybe that's the very kind of summarized version of this.
Well, thank you very much, Matteo, for coming and giving this talk. Super interesting.